All right, so here's a classification task. Another common one, like sorting clothing. These are handwritten digits written down by census takers. And so you want to learn how to read these. So this is really a 5, even though it looks kind of like a 6, and so on. And again, you have data with labels. They tell you what the right answer is. So you split it into training and test sets. And again, you do this bizarre thing that really offends me as a vision modeler. You treat each pixel as an independent bit of data, instead of sorting it into meaningful features like lines or something. And then you can do a fit with just one layer of neurons. And so when you do that and run it, there are various ways to measure the accuracy of it, but if you do it with cross-validation, that's where you split the data into 3 folds, and you train on 2 folds and test on the third, and then you train on another 2 and test on the third, and do that 3 times. And if you do that, you get 95% accurate, 96% accurate, and 96% accurate. However, to be fair, we're not doing a 10-way classifier. This is a binary classifier, just separating into 5 and not 5. So if you just called them all not 5, you get 90% of them right. So 95% right is not as good as you might think it is. But that's what you get this way, and you can express the quality of the result as a confusion matrix here, showing this is how many not 5s are correctly called not 5s, this is how many not 5s are incorrectly called 5s, this is how many 5s were correctly called 5s, and this is how many 5s are incorrectly called not 5s. So you can see the not 5s, it's doing very well at. The 5s, it's incorrectly labeling a third of them, which is pretty bad. So that's why you can't just put one number on it, like 95% correct, and say, there, that's a good representation of how good my model is. It's more complicated than that. There's a thing called precision, a thing called recall, and a thing called the F1 score, which are various ways to measure the accuracy of your system here. And remember, the neurons don't give you yes or no answers. They give you a signal, a gradual varying signal, and you choose what threshold to call. I'll call this a 5 if the signal is above a certain value. So you can adjust that signal. So you can make it really picky, where it will only accept signals that are really high, and then it will never call anything a 5 that's not a 5. But it will now fail to detect a bunch of things that are 5s because they're a little bit off. And the same thing happens, I teach this in my CSSP classes, with biometric authenticators. If you have like a fingerprint scanner or a face scanner to get into a room, you can set the sensitivity really high, and now only the authorized people will get in, but frequently authorized people will be rejected because it doesn't like the way their face looks that day. So you might accept that. If you set the sensitivity really low, then the authorized people will always get in, but now more unauthorized people will pass the test. So you can make this, you can choose which of these you want and make a graph of it, and you'll see as you change the threshold, you can have high recall down here and high precision up here, but you can't have both at the same time. And in biometric quantifiers, they take the crossover point as the measure of the actual quality of your device. Anyway, that shows you some of the issues here, and now you can talk about how to make a 10-way classifier. The original classifier just has one output neuron with a signal. It's just going to be true or false. So how do you do it? Well, one way to do it, there's 2 ways to do it. There's 1 versus 1, and there's 1 versus many. 1 versus 1 will take, compare 1s to 0s, compare 1s to 2s, compare 1s to 3s, and make a whole bunch of them. So you have like 45 models, and then you combine the output of all of them to get the results. And so if you do cross-validation, you get the answer, and then you end up with a confusion matrix like this. This is the predicted label and the true label. The diagonal is the ones that got right. All the other numbers are errors, and you can see errors are not evenly distributed at all. So for example, things that are actually a 1 are frequently seen as an 8. And things that are 5s are frequently seen as an 8. And 4s are frequently seen as 9s, and so on. So this is the more complicated, more thorough description of the quality of your model. So another consideration. All right, let me stop that one.